An unfair coin is tossed n times and n tosses resulted in heads. What is the probability that the next toss will be head? Assume that the probability p of getting heads is a random variable with unknown distribution on 0, 1. Alright, so before we solve this problem, let's define some notation first. So we'll define AK to be the event that we get a head on the kth throw. So this is just the event that we get a head on the kth, that's a t, throw. There we go. And then we'll define a less than or equal to k as the event that we get heads from all the throws from 1 to k, including k. So event that we get heads on throws 1 all the way through k. Okay, and so what do we want to find? We want to find the probability that of a k plus 1, i.e. the k plus first throw is heads. Given that, we know that a less than or equal to k is true, so that we got heads on the first k throws. All right, but so since this is a conditional distribution, this is equal to the probability that of like the intersection of those two events, so a k plus 1 and a less than or equal to k, divided by this probability of a less than or equal to k. This is the definition of conditional distribution. But if we think about this upper term right here, if we get a head on on the k plus first throw, and we got all heads on the throws leading up to k, well, this is just the probability of a less than or equal to k plus 1. If you think about it, right? So we got heads all the way from 1 to k plus 1. That's exactly what that upper thing is saying. And obviously, on the denominator, we still have this probability of a less than or equal to k. And so if we can find this probability, then obviously we'll also be able to find this probability. So let's try to find this probability now. Okay, so let's try to find the probability that the first k throws were heads. So the probability of this a less than or equal to k event. And so notice that if we knew p, if p wasn't a random variable, but rather some fixed constant, then this would just be p to the k. Since we have k throws, and each of those throws, we're assuming they're independent, and yeah, they also have the probability of p of becoming heads, of getting heads. But since we don't know p, we have to use the law of total probability to kind of get an aggregate probability over all possible, all possible values of p. So basically, what that means is we kind of have the probability of this event, so of getting all heads for throws 1 through k, given that p is equal to t. And then obviously we have to integrate over all possible locations of p, since we know p is uniform. The density of p is just 1, so I guess we can just put 1 here. And then we'll integrate over dt to get this final integral. All right, and so as we said before, once we know this probability, we can just write down this probability of the first k throws being head, just t to the k, where t is the new probability now, since we kind of conditioned on this fact. But we take this integral now, which is just t to the k plus 1 over k plus 1, evaluated at 1 and 0, which is 1 over k plus 1. All right, and so we figured out this what this value is. It's just 1 over k plus 1. Let me write it cleaner. All right, and so now we can the numerator will be 1 over k plus 2, since we have k plus 1, and then the denominator will be 1 over k plus 1, which means that this whole thing will just be k plus 1 over k plus 2. And so obviously we're asked to give it for n, so I guess we just plug in n for k. So the whole probability is n plus 1 over n plus 2, and that's your answer. All right, so I hope you enjoyed that problem, and see you next time.